A blessed day, everyone. So, as you can see here, we have moving planets revolving around the sun. Okay, actually, we see motion in our daily lives, like the moving cars, your classmates moving from one classroom to another, your teachers moving from one classroom to another, and so on. So, motion could be in bigger scale. It could also be in smaller like minute things like atoms. Electrons that are revolved around the nucleus serves a certain purpose like releasing radiation, okay, that can be used in other applications. So studying motion is really important, especially in the field of physics or sciences, because okay, that could give us information about how to apply something okay, that we could use in our daily lives in the field of medical sciences, in engineering, and many more. So motion is the change of position over a period of time. So we cannot say that somebody is moving while just rolling their eyes, moving their mouth. So maybe at the perspective of the cell, there is motion, but with the perspective of the person looking at the human being, the person has not traversed a specific distance over a period of time. Therefore, only those that has covered or changed their positions over an interval of time are considered in motion in physics. So there are branches that study motion. Okay, first and foremost is the general, which is called the mechanics. It deals with the study of motion. And under mechanics, there are different branches like kinematics that deals with the description on motion and not focusing on the forces involved in the process. So merely describing the motion itself, the quantities involved like the length, the speed, the distance, displacement, and many more. And to narrow down our topic, we will be focusing only on one-dimensional motion. If we say one-dimensional motion, we are talking about objects that move along a straight line. So we will not be talking in this topic about objects moving in parabolic path or circular path, only on a straight line. So motion in one dimension or motion generally can be represented in many ways. It can be represented through graphs, equations, and even diagrams. So the first here I'm showing you is a motion diagram of a jogger wearing a red shirt. So as you can see, the person has traversed a distance or has changed his position over a period of time. With respect to the tree, okay, it seems like different images are being combined to form series of images. Okay, when you see something like that, okay, you call it the motion diagram. It's a series of images showing the positions of the moving objects at equal time intervals. Now, it's not uh, practical to always use images during our representations. So it could be simpler if we represent those images with a single point. So we don't include the motion of the hands. Kung nagja-jogging, of course, the hands will be moving. The hands or the motion of the hands will not be included. The motion of the feet will not be included. Only the distance being traversed or the change in position with regards to the time also that is used up during the process. So when you use the dots, you call the model particle model. It's a simplified version of a motion diagram in which the object in motion is replaced by a series of single points. It seems like we condensed the person or the object moving into a single point so that when we study about them, it will be easier to remember, it will be easier to represent them. So is there such a thing as negative position? Okay, based on the Cartesian plane, there are variables that could have negative signs like the negative x, which is towards the west, and the negative y, which is towards the south. If the position is located in the negative west, then of course it has a negative sign. If the position is located in the south or towards the south, then the position will have a negative sign. So when will that have a positive sign? When the position of the body or the moving object is located on quadrant 1. So it will have a positive sign in the x, and it will also have a positive y. Now, let's define time intervals. It's equal to the final time minus the initial time. So we represent change with the symbol triangle or delta. Delta t means change in time equals t sub f minus t sub I. F here stands for final, I stands for initial. So final time minus initial time. So in this picture, you can see a jogger again. Let's say the person has started at this point. We have recorded the time here at this point. So it's 2 seconds. And then the time at this point or position is 6 seconds. So what's the change in time or time interval? Let's subtract 6 minus 2. The result is 4. How about displacements? Displacements are vectors that represents change in position. So in equation, that's change d or delta d, delta displacement equals the change or the final displacement or distance minus the initial distance or position. So let's say the person started at 5 and ended at 25. So 25 minus 5 is 20 meters. Checkpoint. Here are the pairs of initial and final positions respectively along an x-axis. Which pairs give a negative displacement? Is it letter A, negative 3, positive 5 meters, letter B, negative 3, negative 7 meters, or letter C, positive 7, negative 3 meters? So if you're going to subtract the values in letter A, the answer is positive 2. In letter C, the answer is positive 4. So only letter B can have the negative displacement because when you add negative 3 and negative 7, the result is negative 10 meters and therefore it has a negative sign. Next is let's interpret position time graphs. If you could recall in junior high school, you learned how to graph points or coordinates. So let's say here we have a record for time and a record for position. Okay, the record in time is 0, 1, 2, 3, 4, 5, 6, and you will notice that they have equal interval. Likewise with position 0, 5, 10, 15, 20, 25, 30. Okay, there is an equal interval in the distance or displacement. So as you can observe, the line formed or the best fit line formed is a straight line diagonal. So diagonal straight line. Why is that so? Kasi the intervals are equal. Therefore, the change is also equal in the graph. So the best fit line indicates the runners or the body's most likely positions at the times between the data points. How about if the line is horizontal? So how will you interpret that kind of graph? So there's no change in position if the line is horizontal. How about if it's descending? It means there is change in position going to 0 or negative or going to the opposite side. So that's how we interpret position time graphs. So at what time was the position of the object equal to 30 meters? So you look for 30 meters. Meter is a measure of distance or position, therefore it should be in the y-axis, and it's here. Okay, so what's the time corresponding to 30? That's 6. So the answer is 6 seconds. What was the position of the object at 4.5 seconds? Okay, so look for 4.5 seconds. And look for the distance or position corresponding that distance. Answer is 22.5 meters. Okay, so we're done describing time interval, displacement. This time, let's differentiate speed and velocity. So if you could recall again, speed tells us how fast an object is moving, and it's always a positive quantity, while velocity contains this information and in addition tells the direction of motion. You'll notice here again in our series of images or motion diagram that the red jogger or the red short jogger has overtaken or has a faster speed because it's the first here in our picture. So the person in red is faster compared to the person in blue shorts. So if you're going to compare the motion diagram or the graph rather, you will notice that the red jogger's line or best fit line is steeper compared to the blue jogger's best fit line. So what am I trying to say? Okay, we can represent the speed or velocity of a certain body using the slope of the graph. So if we're going to focus on the slope of the red jogger, since it's a straight line diagonally, we could choose any of these points in the line and we could get the same slope. So let's say we have chosen this point at 2 meters. That should be our initial displacement and or distance, and our last distance is 6 meters. And that has taken over from 1 second to 3 seconds. Therefore, final displacement is 6 minus 2 for initial divided by 3 minus 1. Answer is 2 meter per second. So the red slope is 2 meter per second, and therefore that is the speed of the body in motion. How about the blue slope? Okay, the final distance here as reflected in our chosen points is 3 and the initial is 2. Okay, minus, if you subtract them, the result is 1 divided by, the time taken is final 3 minus 2 for the initial. It's also 1. So 1 divided by 1 is also 1 meter per second. You'll notice that the slope of the red jogger is 2 higher compared to the slope of the blue short jogger. Therefore, the red short jogger is faster compared to the blue short jogger. So how to get again the average velocity? You just have to get the difference of the displacement over the change in time. Now let's try this. A car travels along a straight road to the east for 100 meters in 4 seconds. Then go the west for 50 meters in 1 second. Determine the average speed and average velocity. So why am I showing you this problem? For you to correctly differentiate speed from velocity. So what's the average speed? Okay, when we're talking about speed, the values will always be an absolute. So you always have to add the distances. So 100 to the east and 50 meters to the west. So that results to 150 divided by the sum or total of the time taken, 4 and 1, 5. So the result is 30 meters per second. How about the average velocity? Since they're going to the opposite direction, and according to the Cartesian plane, there should be a negative position. Therefore, we have to subtract the values 150, the result is 50, divided by 5. Now, in that case, we will not be subtracting the values in the denominator for time because we cannot go back in time. So 5, the result is 10 meter per second. So what's an instantaneous velocity? Lately, we only have discussed the velocity or computed velocity based on the final velocity and the initial velocity. And we did not consider what happened in between. Did the jogger rested at the middle, okay, of the taken time, or the jogger has speed up before we recorded the final distance? So instantaneous velocity is the speed and direction of an object at a particular instant. So what is the velocity at a particular time or at a particular position? Let's say for the red slope here or jogger, that's 2 meters in 1 second. How about at this side? It's 2 meters in 2 seconds, therefore 1 meter per second. So I think it's understandable. So we're done with velocity. This time, let's move on to acceleration. Acceleration is the rate at which an object's velocity changes, or the change in velocity over a period of time. If we could recall again, velocity is the change in this distance over time. Acceleration is the change in velocity over a period of time. And the change in velocity at an instant of time is called instantaneous acceleration. So as you can notice here in our table, we have information for time and information for velocity. If we graph the points, we could see a straight diagonal line pointing upwards. To get the acceleration, we need to get the slope by getting the rise over run or the change in velocity over the change in time, then we can get the acceleration of the body. Therefore, the slope of a BT graph represents the acceleration of the moving object. So the change in acceleration, or average acceleration rather, is the change in velocity over an interval of time or change in. So let's interpret the graph or BT graph that we have here. Find the average acceleration of the train during the following time intervals. 0 second to 5 second. So let's look for 0 second and 5 seconds, which is in between 10 and 0. The final velocity is 10 and the initial is 0. So 10 divided by 5 is equal to 2 meter per second squared. Take note, this is acceleration, therefore the unit at the denominator should be squared. 15 seconds to 20 seconds. So if you are going to look for 15 seconds, it's in between 10 and 20. So the position corresponding there is 10 meter per second. And at 20 seconds, the position is 4. So 10 minus 4 is 6 divided by, 20 minus 15, 5. 6 divided by 5. Okay, of course, that is, cannot go back anymore. I have moved back forward. Okay. Wait for a while. So, 6 divided by 5 is 1.2 meter per second squared. So this time, let's interpret BT graphs. Now in this case, the east and the west are inverted. We're not showing the north and the south. So this could be the south and the the north is at this part. Let's compare A and E. As you notice, they have the same kind of line or best fit line. Since it's horizontal, A and E are horizontal, what can we say about the velocity of the body? It's steady. It's not changing. Therefore, what can we say about the acceleration of the object? Therefore, there's no acceleration because there is no change in velocity. This time, let's compare graphs B and D. You'll notice that they have the same line or best fit line, but they have started at different positions. So if we interpret letter B or line B, it started from the origin and sped up with uniform motion. So you can interpret this as uniformly changing, or the acceleration is uniform. Okay, how about this one? The acceleration is also uniform but has started at the negative position. It came to a stop and then increased again. How about for the line C? It started from a positive velocity at a higher rate and then it descended, meaning it slowed down. So that's how we interpret V and T graphs. So word problems. Suppose you run wind sprints back and forth across the gym. You first run at 4 meters per second toward the wall, then 10 seconds later, you run at 4 meters per second away from the wall. What is your average acceleration if the positive direction is toward the wall? Average acceleration is change in velocity over change in time. Final velocity, of course, is 4 meters per second away, therefore it's negative 4. Plus, or minus rather, towards the wall is positive 4. So minus 4 is negative 8 divided by the time is 10. Therefore, the answer is negative 0.8 meter per second squared. Next, a bus is moving at 25 meters per second when the driver steps on the brakes and brings the bus to a stop in 3 seconds. What is the average acceleration of the bus while braking? So you're asked of the average acceleration, and the formula or equation to solve the average acceleration is change in velocity over change in time. So the initial velocity at this point is 25 meter per second, and according to the first statement, the bus it brings the bus to a stop. Therefore, the final velocity is 0. 0 minus 25 is negative 25 divided by 3 is negative 8.3 meter per second squared. That's the acceleration of the bus. Next, so position with constant acceleration. As you noticed here in our VT graph, velocity is in the y, time is in the x. Now, as you can see, there's an horizontal line here, which represents our best fit line. Therefore, what's the area below that? Okay, so V length, that's the length, multiplied with the width, length times width, equals the area of the triangle below that line. That actually represents the displacement of the moving object or the displacement covered by the moving object. Because we cannot see displacement in the x and y, therefore we can only get that using the area below it. So to get the average acceleration or an equation for average acceleration, we have to add the area of the rectangle below the line plus the area of the triangle. So I have not presented you the triangle, but if you are given with slanting line or horizontally slanting line, you can get an area of the triangle plus the area of the rectangle. So V sub 1 multiplied to change in time is the area of the rectangle. And then this one is the area of the triangle. Therefore, if you combine them, we will result to this equation. D sub F equals D sub I. The I stands for initial, F stands for final. Plus V sub I, initial velocity, multiplied to final time, plus 1/2 of ATF squared. So TF, final time, A is acceleration. So here are the summary of the equations that we will use for uniform acceleration. So equation 1, final velocity equals initial velocity plus the product of acceleration and final time. Final displacement equals initial displacement plus initial velocity multiplied to final time plus 1/2 of the product of A, final time squared. And lastly, final velocity squared is equal to initial velocity squared plus 2 multiplied to acceleration and multiplied to the difference of the displacement. Here are the variables involved that we will use in solving and the initial conditions or the initial variables that are given. So let's practice. A bus starts from rest and accelerates uniformly over a time of 4 seconds for 120 meters. Determine the acceleration of the bus. So let's use the piece method to solve a problem. P meaning you picture out the problem. I get the important information. E, decide what equation to use. C, you calculate. And E, you evaluate. So a bus starts from rest. Therefore, the initial velocity of the bus is 0. And its final velocity is not given. Okay, so the final velocity is not given. Only the time in 4 seconds and the distance in 120 meters. This time, you have to decide among those 3 equations what to use based on the variables given. So the equation to use is this one because it has D, it has V sub I, it has T, and we are asked of the acceleration. So substituting all the values. Okay, so 120 equals 0 times 4 plus A multiplied to the square of 4 divided by 2. Answer is 15 meter per second squared. Next example. A car accelerates uniformly from 21 meter per second to 35 meter per second in 3 seconds. Determine the acceleration of the car and distance traveled. So again, use the piece method to solve the problem. P, picture out the problem. I, get the important information. So here you can get information like the initial velocity, because it's stated here from 21 meter per second. And then final velocity is 35 meter per second. Time interval is 3 seconds. Determine the acceleration of the car and the distance traveled. So the equations that we will be using are two, because we are also asked of two important quantities. That is acceleration and the distance traveled. So for acceleration, we can use this based on the variables given. And for the displacement, we can use this based on the variables given. Plug in all the needed information in our equation, we can get this. Okay, from the first equation, 35 equals 21 plus a multiplied to 3. The answer is 4.67 meter per second squared. The next, Vf squared equals Vi squared plus 2AD. Vf is 35, square that. Vi is 21 squared plus 2, 4.67 is the acceleration based on the first calculation. Multiplied to the displacement, the answer is 83.94 meters. Next. A plane has a takeoff speed of 98 meters per second and requires 1,400 meters, 405 meters to reach the speed. Determine the acceleration of the plane and the time required to reach this speed. Again, using the piece method, picture out the problem. Next, get the important information. So initial velocity is 0 because the plane at that point was not yet moving. The final velocity during the takeoff is 98 meters per second, and the displacement based on the problem is 1,405 meters. The equation to use to solve the acceleration is this one. Vf squared equals Vi squared plus 2AD. And to compute for the time, we will be using Vf equals Vi plus 8. Plugging in all the information, Vf squared, 98 squared equals 0, which is the Vi. Squaring 0 is 0, plus 2 times the acceleration multiplied to the displacement, 1,405 meters. Result is A equals 3.42 meter per second squared. There should be squared, so there's something wrong with my given. There should be square in the second. Vf equals Vi plus 80. 98 is the Vf equals Vi 0 plus 3.42 times time. Time in seconds is 28.65. Now we're done describing acceleration, speed, and velocity. Okay, this time let's move on to free fall, which is another type of or something that involves uniform acceleration. So in the time of Galileo, he was able to show to everybody that objects, regardless of their mass or weight, are going to fall at the same rate. So let's watch this video for us to differentiate and for us to get an idea what happens to objects of different masses when they fall without air resistance and with air resistance.
One, release.
Okay. At that point, you have noticed that without air resistance, objects of different mass fall at the same rate and hit the ground at the same time. With air resistance, okay, that affects the movement of the body falling down. So when we say free fall, we are talking about objects that are dropped from a height. So when objects are dropped, they gain acceleration, constant acceleration, and gain speed at equal interval. Let's say at this position, the speed of the body is 10 meters per second. So at the next point, it has 20 meters per second. Next is 30 meters per second, 40 meters per second. And the change is always 10 or 9.8 meters per second. Therefore, the acceleration is 10 meters per second squared or 9.8 meters per second squared to be exact. So let's have here an example for you to picture out an example of free fall. So in this example, I have not really focused only on the falling body, but a body that is being thrown upward. A pitcher tosses a baseball up along a y-axis with an initial speed of 12 meters per second. How long does the ball take to reach its maximum height? So you have to picture out the problem. There's a boy throwing the ball straight. You have to assume that it's straight upward. So when it reaches its maximum point, it will stop and then start to move downward, increasing its velocity until it stops again when it reaches the ground. So what are the important information you can get from the problem? Initial velocity is 12 meters per second. Final velocity is 0 because when you throw something upwards, okay, there's a time in which it will stop at mid-air, and then of course the final velocity at that point is 0. Okay, that is this point 0, and then when it goes down, it increases its velocity until it stops. So to compute for the time, because you're asked of how long, it means how what's the time taken for that ball to reach that maximum height. Okay, that's VF equals VI plus 80, 12 plus negative 9.8 times time. Why negative 9.8? Let's assign negative numbers for objects thrown upward, since it's opposing to the fall or pull of gravity. The pull of gravity is downward, therefore we will assign positive sign to objects that are moving downwards. And the answer is 1.22 seconds, which means it takes 1.22 seconds for that object to reach that maximum height. A construction worker accidentally drops a brick from a high scaffold. What is the velocity of the brick after 4 seconds? So from the given, you'll know that this is a problem involving free fall. Why? Because the construction worker has accidentally dropped. From the word drop, there's no initial velocity applied, therefore it has freely fallen to the ground. And that took after 4 seconds. And we are asked of the final velocity given VI equals 0 because it started from rest, therefore 0 meter per second, and it took 4 seconds before the brick reached the ground. So equation to use is VF equals VI plus 80. Calculating that, VF equals 0 plus the product of 9.8 and 4. Therefore, the answer is 39.2 meter per second downward. We used here a positive value for acceleration g, or acceleration due to gravity, because that's in the same or parallel with the direction of the pull of gravity, which is downward. And lastly, how far does the brick fall during this time? Using the same given or information, let's compute for the displacement using this equation. Calculating that, the answer is plugging in first all the needed information, you'll get an answer which is 78 meters, okay, along the x-axis or the ground. So we are done with free fall. So here are my references. Let's see each other again for our next topic. Thank you for listening.